A modularization unit is a part of a program that encapsulates a particular function. You store part of the source code in a module to improve the transparency of the program, as well as to use the corresponding function in the program several times without having to re-implement the entire source code on each occasion. See the figure. The improvement in transparency is a result of the program becoming more function-oriented. It divides the overall task into sub-functions, which are the responsibility of corresponding modularization units. Modularization makes it easier to maintain programs since you only need to make changes to the function or corrections in the respective modularization units, and not at various points in the main program. Furthermore, you can process a call as a unit in the ABAP debugger while executing your program and then see the result. This makes it easier to find the source of an error.
With both local modularization techniques, modularization units are only available in the program in which they were implemented. To call the local module, no other program must be loaded to the user context at runtime. Local classes, methods, and subroutines can have the same name in different programs without producing conflicts. This is because the source code for the programs is handled separately in the main memory of the application server. The techniques for global modularization in the ABAP programming language are as follows. Function modules organized in function groups. Methods in global classes. Globally defined modularization units can be used by any number of programs at the same time. These modularization units are stored centrally in the repository and loaded when called into the context of the calling program.
Ideally, the modularization units that are called do not use the data objects of the calling program directly. Conversely, the calling program does not directly change the data in the modularization units. This principle is known as data encapsulation. Data encapsulation is an important aid in developing transparent, maintainable source codes. Data encapsulation makes it far easier to determine where in the program the contents of data objects were changed. In addition, data encapsulation makes it easier to ensure that data within the modularization units changes consistently when, for example, the contents of several data objects within a modularization unit are mutually dependent. As an example, consider a modularization unit in which you process a series of invoice documents. Entering different invoice numbers for invoice items that belong to one another can have serious consequences. It can then be difficult for those responsible for the modularization unit to determine the cause of the data inconsistency.
Parameters are used to exchange data between the program and the module. The total number of parameters in a modularization unit is referred to as the interface or signature. You determine parameters when you define the modularization unit. Parameters are differentiated on the basis of whether they are used to do the following. Pass data to the modularization unit, that is, importing parameters. Return data from the modularization unit to the caller, that is, exporting parameters. Pass data to the modularization unit and return the data after it has been changed, that is, changing parameters. Hint: with subroutines or form routines, only changing parameters and very specialized using parameters are available, which severely restricts your options for controlling data transport. For this reason, use local classes for local program modularization where possible.
A subroutine is a modularization unit within a program. For the ABAP interpreter, a subroutine is always part of the main program. No parameters are used in the example shown in the figure, which makes the subroutine call very simple to structure. A subroutine normally uses values from data objects and also returns values. The next figure illustrates how these variables can be used in the subroutine.
Variables defined in the main program are globally visible within the program and can be changed at any point within the program. This means that subroutines defined within the main program can also change defined variables.
From a subroutine, you can address all global variables defined in the main program. However, to call a subroutine with different data objects for each situation, you must use placeholders instead of global variables. These placeholders are replaced with the required global variables when the subroutine is called. These placeholders are called formal parameters, and together they form the subroutine interface. You need to declare the interface when you define the subroutine. When the subroutine is called, formal parameters must be specialized by means of corresponding global variables or actual parameters. This assignment of actual parameters to formal parameters when calling a subroutine is called parameter passing. The way these main program variables are passed to the formal parameters of the subroutine is called the pass type and is specified for each parameter in the subroutine interface. Pass types for subroutines. Call by value. The system makes a copy of the actual parameter and assigns this copy to the formal parameter. Any value assignments to the corresponding formal parameter in the subroutine, therefore, refer only to the copy of the actual parameter, not to the original. Use this pass type to make the value of a global variable available to the subroutine in the form of a variable copy, without allowing the subroutine to change the respective global variable. Creating a copy of the variable value protects the original. However, creating copies, especially for large internal tables, can be time-consuming. Call by value and result. The call by value and result pass type is similar to the call by value pass type. However, at the regular end of the subroutine, the value that was changed in the copy is written back to the original. When the program is prematurely terminated by a stop statement or a type E user message, the writing back of the value is suppressed. You use this pass type to transfer the value of a global variable to the subroutine and to write the fully processed final value of the copy back to the original. However, it can be time-consuming to create copies and write back values, especially for large internal tables. Call by reference. The system assigns the actual parameter directly to the formal parameter. This means that the value assignments to the formal parameter are carried out directly on the actual parameter. You use this pass type to run subroutine processing directly on the specified actual parameter. It is a useful way of avoiding the time-consuming creation of copies for large internal tables.
In the interface definition, you can list the formal parameters of the subroutine, such as F1, F2, and F3, and type them. You need to specify the required pass type for each parameter as follows. Call by value. List each of the formal parameters that must have the pass type call by value or F1 with the value prefix under using. Refer to the figure for the syntax. Call by value and result. List each of the formal parameters that must have the pass type call by value and result or F2 with the value prefix under changing. Refer to the figure for the syntax. Call by reference. List each of the formal parameters that must have the pass type call by reference or F3 without the value prefix under changing. Refer to the figure for the syntax. Hint: a parameter placed under using without the value prefix also has the past type call by reference. However, this declaration syntax only makes sense for formal parameters that are passed to larger internal tables. These formal parameters are not changed in the subroutine. See documentation under using, but are passed using call by reference to avoid making time-consuming copies.
A formal parameter is typed generically when it is typed using type any or not typed at all. Actual parameters of any type can be transferred to such a parameter. At runtime, the type of the actual parameter is determined and assigned to the formal parameter, known as type inheritance, when the subroutine is called. However, when the statements in the subroutine are not suited to the inherited type, a runtime error can occur, namely type conflict. Only use generic typing when the type of the actual parameter is not determined when the program is created, or when the type of the actual parameter can vary at runtime, that is, dynamic programming. You implement the concrete typing of a formal parameter by specifying a global or built-in type in the type addition. In doing so, you determine that only actual parameters of the specified type can be passed to the subroutine. A violation of the type consistency between formal and actual parameters is detected in the syntax check. The syntax check increases the stability of your program by preventing type conflicts in statements within the subroutine. When you type with the standard types P, N, C, or X, the missing characteristic, field length, is passed from the actual parameter to the formal parameter at runtime. You achieve complete typing with these types, that is, including the field length, by defining and specifying locally defined types. Formal parameters for such data objects must always be typed in order for their components to be accessed within the subroutine. Note: scope kind_name scope P is equal to using or passing scope C is equal to changing.
Variables defined in the main program are global data objects. They are visible and can be addressed in the entire main program, as well as in every subroutine called. Variables defined within a subroutine are called local because they exist in the relevant subroutine in the same way as formal parameters. Memory space for formal parameters and local data objects is allocated when the subroutine is called and is released again after execution. Scope kind_name scope L is equal to local. The formal parameters and local data objects of a subroutine cannot have the same names. When there is a global data object with the same name as a formal parameter or a local data object, the formal parameter or local data object is addressed within the subroutine and the global data object is addressed outside the subroutine. This is the so-called shadow rule within a subroutine. The local data object shadows the global one with the same name. To identify your internal program objects uniquely, use the following prefixes for your subroutine objects: G for global data objects, P for using parameters, C for changing parameters, and L for local data objects. In the syntax example illustrated in the figure, the result of the percentage calculation must be rounded internally to the nearest whole number with 1 decimal place, but nonetheless return with 2 decimal places. To do this, you create a local variable with only 1 decimal place and store the result of the calculation there first. The runtime system rounds the result to the nearest whole number in accordance with the available number of decimal places. When you copy the result to the return parameter, a 0 is added for the second decimal place.
You can use the perform statement to call a subroutine generated in your source code. Define the subroutine and then save your main program. The newly defined subroutine appears in the navigation area. Move it to the required call point in your program by using the drag and drop function. Then replace the formal parameters in the generated source code with corresponding actual parameters. Alternatively, you can implement call generation by using the pattern push button in the ABAP editor. The advantage of generating the call is that it is impossible to forget or mix parameters.
If the current statement is a subroutine call, you can execute the entire subroutine without stopping by choosing the Execute Push button. Processing stops after the subroutine has been completed. In contrast, you can use single steps to stop at the first statement of the subroutine and trace its operations in more detail. If the current statement is located in a subroutine, you can execute the rest of the subroutine without stopping by choosing the Return Push button. Processing stops after the subroutine has been completed. Control functions of the ABAP debugger, including single step, execute, return, and continue, are also available in the classic ABAP debugger and have the same meaning.
Components of a function group. Data objects. Data objects are global in relation to the function group. That is, they are visible to and can be changed by all function modules within the group. Subroutines. Subroutines can be called from all function modules in the group. Screens. Screens can be called from all function modules in the group.
The properties of a function module include a short description of the module and the name of the function group to which it belongs. Similar to subroutines, a function module can contain its own local type and data object definitions. Local types and data objects can only be seen within the function module. The interface of a function module contains the following elements. Import parameter. The system transfers values or variables of the calling program to function modules when the function module is called. During the call, there is no need to supply optional parameters with data. Export parameter. The calling program accepts the output of the function module by way of the assignment of a receiving variable to an export parameter. Export parameters are always optional. Changing parameter. You can transfer the variables of the calling program that are changed by the function module using the changing parameters. Exceptions. Exceptions can be raised by the function module in certain error situations and provide information about the respective processing error in the function module. Exceptions can be handled by the calling program. In general, interface parameters are assigned to types from the ABAP dictionary.
When a program calls a function module, the corresponding function group is loaded and the function module is executed. The function group remains loaded in the working memory until the calling program is closed. When you call another function module of this group, it is processed without being reloaded and with the same global data of the function group. If a function module that writes values to the global data of the function group is called, other function modules in the same function group can access the data when they are called in the same program run. Apart from the global data of its function group, a function module can also access its own locally defined data objects and interface parameters. Interface parameters accept data or return it to the calling program. After you have found a function module, determine whether it has been released from the attributes of the function module. Only with released function modules do you have the right to support and upward compatibility. It is recommended that you use released function modules. You can use the documentation of the function module to determine its functionality and obtain further information. The interface of the function module consists of the import, export, changing parameters, and exceptions. As with subroutines, you can distinguish between pass-by value and pass-by reference. Non-optional parameters must be supplied with data when the function module is called. To find out which additional parameters are to be passed and when, refer to the function module documentation and the documentation for interface parameters.
Features of documentation: short text, functional description, example of use, notes, parameter description, exception description. Function modules that are intended and released for use in other programs should be documented. A distinction is made between function module documentation, which describes the function of the module, and parameter documentation, which tells you how individual parameters or exceptions are used. You can access the function module documentation by choosing the F-Module Documentation push button. Click on the displayed links to go to the parameter documentation only in display mode. You can also access parameter documentation by choosing the push button for the respective parameter in the long text column. The green light indicates that documentation has been created for the parameter. If you are unsure whether the function module does precisely what you want it to do, you can test it in the test environment prior to installing it in your program. An input template allows you to specify values for the import and changing parameters. To check values during runtime, you can also switch to debugging mode. The values in the export and changing parameters are listed after execution. If the function module triggers an exception due to an error, the exception is displayed, where applicable, with its message text. The function module also displays the runtime. These values are subject to the same restrictions as the runtime analysis. Therefore, repeat the tests several times using the same data. Store test data in a test data directory and create test sequences.
In the call syntax, you need to specify the name of the interface parameter or formal parameter on the left side of the parameter assignment and the data object, or the value of the calling program or actual parameter on the right side of the parameter assignment.
To avoid spelling errors, use the pattern push button to generate the call when you implement a call in the source code. Alternatively, you can display the function group in the navigation area and drag and drop the function module into the ABAP editor area to generate the call in the source code. This generates the entire call syntax, which lists all interface parameters as well as exceptions. Optional information is commented out in the call. Afterwards, you need to fill in the actual parameters and, when necessary, implement exception handling. If application errors occur when a function module is processed, for example, a value is not suitable for the calculation, the function module raises a corresponding exception. The exception cancels the processing of the function module and returns the system to the calling program. If the exception is listed or caught in the exceptions block of the call, the specified return code is entered in the SY sub-RC system field of the calling program. By checking this field after the call, you can determine when and where applicable, which exception was raised so you can react accordingly. If no exception is raised by the function module, the SY sub-RC of the calling program is set to 0. You also have the option of setting a return code explicitly for some of the possible exceptions and setting a different return code for all unmentioned exceptions. To do so, list the formal exception, others with the desired return code. Catch all exceptions in your call and react to them in the program. If a raised exception is not caught, a runtime error occurs.
When you choose the Display Push button, a pop-up screen appears in which you need to select whether to create the function group. In the following module dialog box, enter a short description and choose Save to create the function group.
To create a function module, proceed as follows. On the SE80 screen, right-click the function group that is created. From the context menu, choose the menu path Create Function Module to create a new function module. In the module dialog box, enter a short description and choose the Save Push button to create a function module.
After defining the corresponding importing and exporting parameters, you can switch to the Source Code tab page to implement the functions of the function module. Hint: the comment block directly under the keyword function is created by the function builder and is changed when changes are made to the parameters.
The Business Object Repository or BOR in the SAP system contains business objects. A business object is a class and corresponds to an SAP table or a table hierarchy. A business object has BAPIs as methods. You can call these BAPIs to access the corresponding table or tables. A BAPI is a means of accessing data in the SAP system. BAPIs usually exist for the following functions of a business object: creating an object, retrieving object attributes, changing object attributes, listing objects. The functions of a BAPI are encapsulated in a function module that can be called remotely. BAPIs can therefore be called by RBAP programs of the same SAP system as well as by external programs.
The figure shows how BAPIs can be used. You can use the BAPI Explorer to list business objects as well as the corresponding BAPIs with reference to the application. To call the BAPI Explorer, use the following path in the SAP Easy Access menu: Tools, Business Framework, BAPI Explorer, or Transaction BAPI. After you have located the required business object or BAPI, you can display the relevant details on the right side of the screen by selecting BAPI. You can navigate to its display using the function builder by double-clicking the displayed function module. Function modules for BAPIs must fulfill the following technical requirements: naming convention, BAPI, business object name, method name, remote enabled, no user dialogues or messages. Name prefix for BAPI structures, BAPI. Interface parameters are typed with components of structures from the ABAP dictionary created for this BAPI. No changing parameters until release 4.6. Raise no exceptions. Errors are reported to the user through the special export parameter return.
To use a BAPI within the same SAP system, you need to call the relevant function module directly. Note the restrictions mentioned in the Properties of a BAPI Function Module section. Hint: BAPI interfaces are created according to external call requirements, that is, a call from an external system. Amounts are therefore expected in an external format with 4 or 9 decimal places. During the call, the amounts must be transferred to the interface in an appropriately converted format, even when the corresponding currency has no decimal places. For this conversion or reconversion, you can use function modules from the BACV function group inside package SBF_BAPI.
Before using global classes and methods, you need to know some basic terms used in object-oriented programming. You have read about function groups that make reusable units available in the form of function modules. Object-oriented enhancements to ABAP have introduced the use of global classes, which make functions available in the form of methods. Similar to function modules, methods have an interface known as a signature that comprises import, export, changing parameters, and exceptions. Classes have other components in addition to methods. For example, classes contain global data objects known as attributes. In the same way that all function modules can access the global data objects in a function group, all the methods of a class can access the attributes of that class.
Global data objects within the function group are not visible outside the function group. This is referred to as encapsulation of data in the function group. Attributes are normally encapsulated in the class and can therefore only be read or changed using methods of the same class. In contrast to function modules, classes allow you to make specific attributes visible to users of the class. A distinction is therefore made between public and private attributes. You can apply the public and private distinction not only to attributes but also to methods, whereas all function modules can be called from outside the function group. Only public methods are available outside the class. Private methods can only be called by methods of the same class and are similar in this respect to subroutines within a function group. The major difference between global classes and function groups is that a function group with global data objects can only be loaded to the program context once for each main program, whereas a global class can be loaded as many times as you like. This is known as multiple instantiation of the class. Values in the global data objects of a function group are the same for all function module calls. By contrast, a class can have several instances, also known as objects, each of which is stored separately in the program context of the main program. Each instance can therefore have different attribute values. Consequently, a method sees different values in the attributes depending on the instance for which it was called. You need to generate a class instance explicitly in the ABAP source code using the createObject statement.
A distinction is made between static methods and instance methods. The main difference is that an instance method can only be called when a class instance is generated beforehand. By comparison, static methods can be called without any previous instantiation of the class.
With other repository objects, the display and processing of global classes is incorporated in the Object Navigator. You have several options for opening a global class. In the navigation area, for example, choose Class/Interface and enter the name of the class in the input field directly under the name. You can also display the object list for a package first and then double-click the name of the required class in the subnode Class Library Classes. Choose the Attributes tab page to open the list of attribute definitions in the class. If you only want to use the class, only those attributes that are public are of interest. You can address these attributes directly outside the class.
Choose the Methods tab page to open the list of all method definitions in the class. With methods, only entries that are identified as public are of interest to the user. Only these public methods can be called externally. All other methods are used for modularization within the global class. A method identified as a static method can be called directly without the need to first generate an instance of the class. With instance methods, you need to generate an instance and then call the method specifically for that instance. Under normal circumstances, the instance method then accesses instance attributes that contain different values for the various instances.
Parameters for a method are displayed in a separate window. You access the window from the method list by placing the cursor on the required method and clicking the parameter push button. In contrast to function modules, there is no separate list for export, import, and changing parameters. Instead, the parameter type is entered in the type column.
You need to navigate to a separate display window to display exceptions for a method. You access it from the method list by placing the cursor on the required method and clicking the Exceptions push button. BASIS Release 6.10 introduced class-based exceptions in ABAP. Handling these exceptions is very different from handling the classic exceptions of function modules. A method can either raise only new class-based exceptions or only classic exceptions. It is not possible to mix both concepts. A checkbox shows you which exception concept is used by the respective method. While the classic exception concept allows you to choose any exception identifier, with the new exception concept, you have to specify the names of special classes, the exception classes. Hint: the class-based exception concept is also available for function modules.
With global class documentation, a distinction is made between the documentation of the class as a whole and the documentation of individual components. You can access the class documentation by choosing the Class Documentation push button. To consult the documentation for an individual method or attribute, navigate to the corresponding list. Select the required component with the cursor and choose the Documentation push button.
You use the call method statement to call a method, and you then specify the method. You need to distinguish between an instance method and a static method. With static methods, this specification comprises the name of the class and the method, separated by the static component selector double header arrow. The parameters are then passed to the function module call in both an exporting block and an importing block. Methods can raise either classic exceptions or class-based exceptions. Classic exceptions are handled in the same manner that you encountered with function modules. Classic exception handling. In the exceptions block of the method call, the system assigns a return code to the exception. When the method terminates with this classic exception, this return code is placed in the system subrc system field. By querying system subrc, the calling program can react to the exception. In comparison, handling class-based exceptions is much more complex. Class-based exception handling. The call must be bound between the try and end try statements. The exception is then handled in a processing block that begins with a catch exception class statement, where exception class represents the exception class that is to be handled. If the corresponding exception is raised within the try-end try block, processing is terminated and the system branches directly to the relevant catch block. If you generate method calls by using drag and drop function or by using the pattern push button, the system generates the statements for handling the class-based exceptions as well. You then need to remove the comments and implement the catch block.
Reference variables are defined using data reference name type reference to class name. When the program starts, a reference variable still has its initial value. It does not point to an instance. After it has been used to create an instance, the reference variable no longer has the initial value and points to that instance. You can use the createObjectReferenceName statement to generate an instance of the class that was specified in the definition of reference variables. Afterwards, the reference variable points to the newly created instance. When you use createObject, you may need to supply the import parameters of the special method constructor with data. This special method is automatically executed immediately after the creation of the instance. With its import parameters, this special method maintains the corresponding attributes of the new instance. You call methods of an instance using the call method reference name, method name statement.
To create a global class, open the context menu for your package in the navigation area and choose Create Class Library. Class. In the dialog box that appears, enter the name of the class, a short description of the class, and several other properties. After saving your entries, assign it to a correction in the usual way. Alternatively, you can choose Class/Interface from the drop-down list in the navigation area. Enter the name of the new class in the field below it and choose the Display Push button. Confirm that you want to create this new class.
To create the static method, simply enter the method name in the method list. You can maintain the visibility and type of method, either static or instance, using the corresponding input help. To create a parameter for a method, branch to the parameter list for the corresponding method. Switch to change mode and enter the name of the parameter in the list. Use the input help to maintain the parameter type, such as import, export, and so on, and specify an associated type. To implement the source code for a method, select the method in the method list and choose the source code push button. Implement the source code between the method, method name, and end method statements. While you are editing source code, you can display the method signature method. To do this, choose the signature push button as shown in the figure.
The figure shows how to create a local class in the source code of the program. A distinction is made between the definition block and the implementation of the class block. The description of the attributes and signatures of the methods are located in the definition block, whereas the implementation block contains the source code of the methods. You can define the class end class statement locally in the program. Just as the type statement defines local data types, the class end class statement defines local object types. The definition block is divided into several sections in which the public and private components are defined. For example, public section and private section.
The figure shows a schematic representation of how a public static method is defined and implemented. The method is public because the definition is located in the public section of the class. To define an instance method, as opposed to the static method, the methods statement is used instead of class methods.
The syntax example shows how to define a local class with a static method as displayed in the upper right section and how to implement the method as displayed in the lower right section. In the section on the left, you can see the static method call from the main program. Notice that the call is identical to a static method call in a global class. You can define the local class directly in the definition block of the main program or in an include statement. Hint: you need to define the local class in the sequence before the call. The local class behaves differently from a subroutine here. You can define the subroutine after the call.